In Cycle 2, Lesson 5, we're going to carry on talking about the inverse of a function, and in particular, we're going to look at a quadratic function in this lesson. So let's just remember, first of all, what an inverse function does. It's the opposite of a function. It undoes an original function by doing the opposite operations in the opposite order. And we represent an inverse function by, pardon me for dragging my iPad around a bit, we represent an inverse function by writing f at f to the exponent -1 at x. And that little -1 exponent tells us that we're dealing with an inverse. So to graph an inverse function, we know that we can take the original function, the graph of the original function, just switch all the x's and y coordinates, and then we'll have our graph of the inverse. And it'll look like it's reflected in the line y equals x, that diagonal line through the origin. To get the equation of the inverse of a function, we switch x and y in the original equation and then resolve it for y. And the graph of an inverse, so I guess I already said this point up above, the graph of an inverse is a mirror image in the line y equals x. So let's just jump into our first example. If we have the function f at x equals x squared, we know that's a parabola, right? So let's graph that using a table of values. So it looks like I've given 2, 4, about 10 different points we could fill in. Well, let's just start at -3. So if I pick these different x values, I don't know if I'll need all the space here, but if I start at -3 and go up to +3 on the x-axis, when I plug those different values into f at x equals x squared, we know at this point that we put the different x values in to the equation. In this case, putting it in the equation means squaring it. So -3 squared is 9. -2 squared is 4. Positive, right? Because -2 times -2 is +4. 1, 0, 1, 4, 9. And we could do other ones. I mean, they're not going to have room to graph them, but if I had 4, I'd get 16. 5 would give me 25. 6 would give me 36, and so on. There's no way I'm going to be able to graph all those on this grid to my right, but there you have it. So if I want to graph it, we know we got these points 0, 0. Well, if I'm starting from let's just do them from the table of values. -3, 9, well, that's off the graph. Can't do that one. -2, 4, yeah, I can graph that one. That would be this point here. And -1, 1, that would be this point. And 0, 0, and 1, 1, and 2, 4, and then 3, 9, well, we're off the graph again. So I can't graph all of these points, but we can see how they would work. So there's the graph of y equals x squared, or f at x equals x squared, using function notation. Now, if I want to graph the inverse, the easiest way to do is just take all these ordered pairs and switch them. So we have this point, for example, -2, 4. If I switch the x and y coordinates, I get the point 4, -2. And so 4, -2 is a point over here, right? Here's 4, -2. And if I took this point -1, 1 and switch the x and y coordinates, I get the point 1, -1. So I get this point here. And then 0, 0, when I switch them, I still have 0, 0. The point 1, 1, which would be this one here. When I switch x and y coordinates, I still have 1, 1. So that one doesn't go anywhere. And then the point 4, 2, 2, 4 becomes 4, 2. And I get this point over here, 4, 2. And so then I've got what looks like a sideways parabola. And again, it's reflected in the line y equals x. So if I was to just draw a dotted line like this, then this is what we're reflecting the function in. Notice how these 2 points here never moved. And that's because they're on the line y equals x. Any point that's actually on the line y equals x, when we reflect it, is still going to be on that line. That's why those 2 didn't move. But all the other ones are mirror images across that line. State the domain and range of the original function f at x. Well, it's a parabola. The domain is all real numbers. And the range is all real numbers greater than, where y is greater than or equal to 0. The domain and range of the inverse, well, as you can see on the x-axis, this function is only starts at the origin and only goes to the right. So the domain is all real numbers where x is greater than or equal to 0. It can't be negative x values. And the range, it goes up forever and down forever following, if I was to go out far enough, I could get to any y value since it's a sideways parabola, and it's just YER. So what we've noticed up till now is that switching x's and y's will get us our new points. Switching x's and y's, as we're told above, will get us a new equation. It turns out that switching our domain and range is true as well. So the domain of the original function became the range of the inverse function, right? XER, YER, we had to switch x and y, but it's all real numbers. And the range of the original function became the domain of the inverse function. The range was all real numbers greater than 0, greater than or equal to 0. The domain became all real numbers greater than or equal to 0. So that too switches, which makes sense since domain just deals with x values and range just deals with y values. Switching x and y for them too would switch the domain and range. Is f to the negative 1 of x a function? In other words, is the inverse a function? Looking at that red graph there, it's pretty clear it's not a function. It would fail the vertical line test. There are many points that have two outputs for one input, two y's for one x. Given f at x equals 2 times x plus 3 squared minus 4, find the inverse by switching for x and y and solving for y. So we've done that before, mostly on linear functions, so let's see how it works for a quadratic function. So I'll just rewrite the function, first of all, using y instead of f at x. So I'll just do a quick replacement there. And then I'm going to switch x and y because that's how we do it. So now I'm going to write x equals 2 times y plus 3 squared minus 4. And my goal is to isolate y, right? To get y by itself. So I have to do reverse order of operations. Reverse operations in the reverse order of operations to do that. So the first thing I'd have to do is I work from the outside in. I'm going to have to add 4 to both sides. And then the next thing I would end up doing is I'd divide both sides by 2. And now we get to the squared. So the opposite of squaring is taking the square root. So I'll take the square root of both sides. When I take the square root of the left side, it looks like this, but I need to put plus or minus in front of them because, again, anytime we choose to take the square root of something, we have to consider positive and negative solutions because both negative and positive answers, when squared, would give me what I started with. So there's actually 2 answers for any square root. When I take the square root of the right side, that cancels out the square, the exponent 2, and I'm just left with y plus 3. And then the last step is I'm going to subtract 3 from each side. And it doesn't really matter which order I write it in, but what is important is that plus 3, since it's happening now after I've done the square rooting, should not and absolutely cannot be written underneath the square root sign. It needs to be outside of that square root because it's happening after we take the square root. And then when I put it all together, I can rewrite it in inverse function, in function notation, and I'll just write inverse function of x is, I could write it like I have there. Sometimes I like to just put the whole number first, so I might rearrange the order a bit and just put the minus 3 first, do minus 3 plus or minus the square root of x plus 2 over 2. That doesn't matter, but what does matter is, once again, the negative 3 is not under the square root sign, and I absolutely do have the plus or minus there. Also, make sure that you're writing the square root sign all the way down to the bottom like this, and not writing it like, I sometimes see it like this, because this is not the same as this. The one I crossed out tells me to take the square root of x plus 2 and then divide by 2, whereas the one I've circled tells me to do x plus 2 divided by 2 and then take the square root. So it's a completely different order of operations. So by not extending the square root sign down to the bottom of the fraction, you're writing something different, which would not be correct. What restrictions on domain of f at x are necessary to make the inverse a function? So, well, let's take a look at the graph. We know how to graph something in vertex form easily. So let's just do a quick little sketch of the graph and its inverse. So the original function, which I'm highlighting now in green, has its vertex at -3, -4. So I'm just going to estimate that that's about here. It's got a vertical stretch of 2, so it's going to open upwards. Positive 2 is opening upwards, and it's been stretched a little bit, so it's a bit skinnier looking than maybe your average parabola would look like. So there's f of x. The inverse, as we've seen, we're going to switch the x and y coordinates, and so the vertex of -3, -4 would become -4, -3. So we get this vertex of the sideways parabola, let's say somewhere around here, maybe not quite that high. I don't have a scale on here, so I'm just estimating. Let's say that's -4, -3 there. Every point is going to be reflected in this line y equals x, right? The line y equals x is this one here. So every point on the graph is going to get reflected. So, for example, this point that would be around here is going to be reflected across to maybe a point that's here. And this point that would be about here is going to get reflected across that green line to a point that's maybe over here, right? And let's go take this x-intercept here. That's going to get reflected across the x-axis, or across that dotted green line, to be on the y-axis. That would be somewhere down here. And this point, that's this x-intercept here, again reflected across that dotted green line, I'd get a point about here. And if I kept going point by point, I'm going to end up with this sideways-looking parabola that's the exact same shape as the original function, but it's turned on its side. Clearly, the one I've drawn in red, the inverse function is not, or the inverse is not a function, right? It's going to fail the vertical line test multiple times. If I want to make it into a function, an easy way to do it is just to take half of it. Maybe if this is the vertex here of my sideways parabola, say I just took the upper half. Well, the upper half of this came from the right-hand half of the original function. So I can make my inverse be a function if I just cut my original function in half along the axis of symmetry, is really what it boils down to. So again, the vertex for the original function was from the equation -3, -4. So the axis of symmetry has to be x equals -3. So if I restrict my original function so that it's greater than -3, or it could be greater than or equal to, that doesn't matter if I include the vertex, that will make it so that I only have the upper half of the sideways parabola for my inverse. Likewise, I could also take the lower half, right? Because this lower half of the function, trying to find a different color. Let's do this in purple. The lower half of the function came from the left-hand side of my original function. And so I could also do x, I could restrict it to just doing the x less than -3. So, but if I want to get as much as I can without making it not be an inverse, the axis of symmetry would be the place to do it. So I could make my domain of f at x for my original function be all real numbers, but only take what's greater than or greater than or equal to. Again, I can include the equal sign or not. In this case, it doesn't matter. -3. And again, -3 is the important number because that is my axis of symmetry on my original graph. That's what's going to cut my original graph in half. If my vertex was somewhere else, I'd take the x-coordinate of whatever that vertex was. So there's a couple possibilities. Take either greater than -3, or I could do less than -3. Oops, not y though. And again, I could include the equal sign or not. All that does is include the vertex or not, but it'll still be a function whether I include it or not. So following that exact same idea, what restrictions on the domain of the given graph are necessary to make it into a function? So based on what we just talked about, if I recognize that the axis of symmetry goes down here through the vertex, the axis of symmetry would be x equals -5. That would cut this parabola in half. I'd have a left-hand part, which when I did the inverse of it, would look like, let's see, we've got this vertex at -5, -2, so -2, the vertex, so it would be over here, so the left-hand half would sort of look like this. And that would be a function, right? If I only did the domain of my original function was all real numbers that were where x is less than -5. That would give me that red graph. I'll circle it in red. Or I could do the blue one, as they show there. If I did that, I'd only get the upper half. And the blue one comes from doing my domain be greater than -5. So again, it's that axis of symmetry that I'm looking at as my cutoff point. Above or below it will cut the parabola in half so that when I do the inverse is going to be a function. I don't need to do both. Again, I'm just showing options. Either one is correct. Both are correct, but this question's only asking for one. Anyway, so that's it. Some specific things about doing inverses of quadratic functions. Take a look at the homework.